Yes, I'm Aaron Ames, and so yeah, as she pointed out, I'm really going to be talking about the seeds of what a lot of what I want to be pursuing actually in the next 5 years, and some results in that sense. So things are kind of pieced together, but I think you're already starting to see there's a very nice flow here. And the flow we're going for is going from human walking to hybrid systems or mathematical models, and then from there to robotic walking, and then hopefully back to human walking. And I'll explain all this in much more detail. I try to be a little light on the math because I think the big picture ideas are much more important. So first, what's the goal of this in general? The biggest level goal is human-like bipedal robotic walking. Why do we want human-like bipedal robotic walking? Well, I think for me, it's cool, and that's it. I mean, that's a good enough reason for me. But that's not good enough for everybody. So there's actually lots of real reasons why you want that. It's interesting because these are actually, I've kept this the same since my job talk 2 years ago, and these have not changed at all, in fact, because these are all very relevant right now. Space exploration. In fact, NASA is currently working on a bipedal robot that they want to launch to the moon and Mars to walk around with a torso on it and take samples and do data. Military applications, exoskeleton design, things like that become very important to understand how you do walking. Elderly assistance, rehabilitation, prosthetics. Basically, the idea here is if you can understand walking at its fundamental level, you can do lots of things with that. And the way to really know if you understand walking at a fundamental level is make robots walk. Because there's no cheating here. You know? You can't, if you put things on humans, the humans can compensate for a lot. But if you can get something going all by itself, you really understand it. Of course, there's different qualities of walking that we're looking at. Everybody's seen Asmo, and people might say, oh, well, it walks, so we're done, right? But not really. If you've seen Asmo and the way it walks in a very statically stable fashion, okay? So when it walks, I can even mimic the walk pretty well. And you can do this too. At any point in time, keep your center of mass over your foot, and as you walk forward, right, you get exactly the Asmo walk, okay? And so that's statically stable, meaning that if you freeze that walking at any point in time, it won't fall over, right? But humans walk dynamically stable, right? Which means that when we walk forward, if I froze halfway here, I'd fall over. It's that dynamic stability aspect that really creates human-like walking. And this has been explored by a couple people. These are actually 2 pictures of robots that were at least controlled by somebody in Michigan, Jesse Grizzle. We've done a lot with this. They're all 2-dimensional robots, meaning that there's no side-to-side motion in the plane that's supported by a boom to keep them up. But the walking is good. It's good. It's better than Asmo, but it's not good enough yet. And I think even Jesse Grizzle of Michigan will admit to that. So the idea is, what can we do here? And this is actually a shot of what we're going for. This is the robot we're designing right now in my lab. And how do we get walking for that? All right, so obviously since we're using human-like bipedal robotic as walking as our goal, what are we going to do? Well, we're going to use human walking to motivate hybrid models and controllers. So we want to look at humans and try to understand how they walk at a fundamental level. And then that will give us human-like walking, right? It's pretty self-explanatory. So what I'm actually going to mention in this is this experiment I did at Berkeley this summer with some sensors on human walking and how we're using that to actually achieve good robotic walking. So we'll go through all that. But first, a little bit of history. So I mentioned Asmo and static stability. Now again, human-like walking is with dynamic stability. So when did that really start, that idea of dynamic stability? Well, it actually didn't start that long ago. The first dynamically stable walker to ever really be invented was only 30 years ago, in 1990 by McGeer. And basically the idea is, this actually isn't his walker, but it's a replica of it. I gave this a similar talk to a conference, and the person who was there that built that was very, very clear to point that out to me, which was very amusing. But the idea, what he discovered, is that if you build robots that look like humans pretty much, okay, mechanically, and you push them down a shallow slope, they actually will walk stably. So it seems like walking is intrinsic to the way we're designed, mechanically. Okay, which is really, it was in some sense, this is one of these ground-shattering results where people are like, wow, you know? But there are problems with that. The problems with that is that mechanically that works. It shows there's something intrinsic mechanically to walking, but it doesn't tell us anything about how walking actually works. Okay, and we can't have everything going downhill all the time. And these aren't particularly robust. So things have been done to try to add little controllers on there to try to mimic this walking actively. So I'll actually show you the Collins walker here. So the Collins Walker was actually built by an undergrad. This should give you guys some expectations. Very impressive. And this is it walking statically, or I mean walking without actuation down a shallow slope. And you see it's very almost human-like looking for mechanical design, right? No control here. So it's pretty impressive. And they actually added a little control and made it walk on flat ground a couple times. But here comes the problem, is when you only look at mechanical solutions, you don't understand the underlying problem. And so they actually had to walk a couple times, and then they tried to make it more robust, and it never walked again. You know, so it's one of those things that if you don't understand what's really going on, you can build something one-off, you can tune parameters, but you'll never be able to make something repeatable. All right, so that was really the goal with this next thing, which is this biped built by Jesse Grizzle of Michigan, and the idea here was to really mathematically understand how to make this happen. But again, there was not a connection back to the mechanical nature of walking. So this is actually, unfortunately, this is a movie of Rabbit, but the walking is quite similar as we load up all these codecs. So if you look at this walking, this is very mechanical walking. You see it is dynamically stable because there's nice steps being taken, but it doesn't look as good as that walker built by an undergrad, right? Really? The difference here is we formally understand why this is walking. We get all the math behind it, we can make it repeatable, and we can do it again and again and again. So there has to be some good compromise between, human-like walking passively and actuated walking. So that's kind of the idea behind all this work, is that we can understand the fundamental mechanisms we can get this human-like walking. All right, so what's the big picture on this whole thing? I mean, I could go on philosophizing for days, but what am I going to specifically do? Well, the idea is you look to humans first. Okay, and you look to humans and look at humans that efficiently walk. Okay, you take that data and you create mathematical models of these systems. All right, representing the human. And I'll talk about this quite a bit in this experiment I did and how we got some data there. And then once you have a model, you build controllers for it. Now again, these controllers that you build should be based on how humans walk. Okay, if you do analysis, you can bring it back to this formal math and verify that it's doing everything you want it to do. And then if you do all this right, you should get back to human-like walking. And in the meantime, you can make stops at things like prosthetic design. You can build great bipeds. You can take those controllers and put them on a prosthetic and get great walking with prosthetics. So the way we have to formally go about modeling these systems is bipedal robots are naturally hybrid systems. So they're more complicated than the things you traditionally see. What you traditionally see is, let's say, Newtonian equations, right? Or Lagrangians. These are continuous dynamics. Okay, but every time the robot strikes the ground, there's an impact on the system. And it causes a jump in the velocity of the system. So there's these discrete jumps. So this combination of continuous Lagrangian dynamics and impact mechanics. So in the end, you combine these, you get hybrid dynamics. So I'll explain that in more detail. But what are we going to do in this control, in this presentation, is we're going to talk specifically about, after we get these models, some ideas for how you can obtain walking in them. So we're going to begin with 2D, and what we're going to do is actually kind of try to merge this passivity-based approach, which is this mechanical walking you saw in this Collins Walker, with human-inspired controllers. Now, the stuff I'm going to present is very cursory, and we've actually been doing some very recent results that are very nice, and I'll show you the videos of those, but they're not ready for prime time yet. They're not ready for presentation yet. So you'll see some of how we're getting where we're going, and we'll talk really briefly about how we can bring this to 3 dimensions. And 3-dimensional walking is actually very complicated, so this will be very high level, because trying to go through the details of that is difficult. So going back to the human data now, I'm doing a time check. This is our big picture. So what we're going to do is we're going to specialize to this little bit of this diagram that we have. So what we're going to do is we're going to start with human walking data, and we're going to use constraints to determine the hybrid model. And what I mean by constraints is, what we're going to do is we're going to look at a person walking, and we're going to look at what contact points are in the ground, or touching the ground at any given time. It turns out that actually completely determines a mathematical model for the system when you do that. So what we can do then is we'll consider a 3D biped that we've been studying, and show how this model is at least in some ways related to this bipedal model itself, how we can use the human data to, in some sense, construct this model, and we'll give some more details about that. All right, so I always have to throw this slide up. Every talk I ever give has this slide on hybrid systems. I'm going to throw a lot of math your way, and then you're not going to see that much math for the rest of the presentation. But I think it's important to kind of see that this is the mathematical object we're fundamentally working with. Okay? And rather than looking at all this math, because